In the last chapter of the notes, we talked about developing theoretical models for chemical and biological processes. We did this by writing conservation of energy and conservation of mass equations. In this chapter, we will introduce more general balance equations. We'll also talk about rate equations, equilibrium equations, and boundary conditions as constituents of theoretical models of chemical and biological processes. The balance equations are either conservation laws or transport equations. You know from CBE 101 that a general balance equation states that the accumulation of a quantity is equal to its net transport into the system through the system boundaries, plus the net generation of that quantity within the system. This can be written for any extensive quantity. It could be mass, it could be molecular species, it could be thermal energy, it could be Reynolds stress. It can be written around any bounded volume, like the contents of a reaction vessel or a human heart. We'll talk more about the type of volume in a moment. The net transport and net generation terms on the right-hand side of this equation can include multiple routes or phenomena and mechanisms, and they can be quantities that are either greater than or less than zero, which means that the accumulation can also be greater than or less than zero. In the general sense, the volume around which we write the balance equation does not need to be well-mixed, homogeneous, or even fixed in space. Sometimes balance equations are written for extensive quantities that are conserved by chemical and biological processes. For conserved quantities, there is no net generation or consumption, because conserved quantities are neither generated nor consumed by chemical and biological processes. Conserved quantities include things like total mass, total energy, atomic species, electric charge, linear momentum, and angular momentum. These are very important types of quantities. But there are many other quantities of interest that we might want to write balance equations for. When we write balance equations for non-conserved quantities, we call them transport equations, and they can include net generation or consumption. Many models in chemical and biological engineering are based on balance equations for four main types of quantities: chemical species, mass, thermal energy, and momentum. So in the notes for Chapter 3, we'll develop balance equations for these quantities. The net transport of a quantity can occur by two different types of mechanisms. The first type we call convection or advection. This occurs when the quantity of interest is carried along by the moving fluid in the direction of the bulk fluid flow. Now, the term convection can mean lots of different mechanisms of transport. And it doesn't always mean transport in the direction of the bulk flowing fluid, depending on the context. So to be specific, we'll call this type of transport advection. Diffusive transport, or diffusion, occurs when the property is transported due to some gradient. Diffusion is described by transport rate laws that we'll discuss later in this chapter. The balance equations are always written around a system which we call a control volume. Control volumes can be one of three different types. The first type is called an Eulerian control volume, and it is represented by a fixed volume of space that does not move. So the contents of this reactor could be a control volume, or the contents of this distillation column could be a control volume, outlined with the blue solid line. Although material enters and leaves, the contents of the reactor are fixed in space. A material or Lagrangian control volume, on the other hand, is a control volume that represents a fixed amount of matter. That amount of matter may deform or move through space with time. So here's an example of a material flowing down a pipe, and we draw a blue box representing a material control volume at a particular point in time. At some later point in time, as the material has moved through space, that control volume may be deformed into a different shape and be in a different location, but the same material remains in that control volume as it moves through space. The third type is a general control volume that is neither fixed in space nor containing a fixed amount of matter. Nonetheless, the general control volume is still useful, typically because the control volume itself can be easily defined by some interface representing a bounded volume. For example, we might consider the lungs of an organism to be a control volume. The lungs are not fixed in space. Their size may change as the organism inhales and exhales, nor do they contain a fixed amount of matter. Air enters and leaves the lungs, and blood enters and leaves the lungs through blood vessels. In fact, if the lungs didn't change their shape or didn't have material entering and leaving, they would be pretty useless. Another example of a general control volume is this gas bubble, which may be in an absorption or stripping operation. The gas bubble rises through a liquid, so it doesn't remain in the same location, and solutes are exchanged across the boundary of the bubble. That's the purpose of the bubble. So it also does not represent a fixed amount of matter. Nonetheless, it is defined by a clear interface, and it may be useful for us to describe the transport processes across that interface. In the next video, we'll develop a generalized balance equation that can be used for any extensive quantity for an Eulerian control volume.